So, as I understand it, the purpose of these talks is to tell people in the rest of the programs what's exciting about the other programs. And so I thought what I would want to explain about the Higgs to friends in quantitative immunology. Actually, I mean, of course, as you all know, there's been an enormous amount of excitement about the discovery of the Higgs, or sorry, the politically correct thing to still say is the discovery of the Higgs-like particle. Accompanying this has been a whole slew of different kinds of metaphors and analogies that people have used to try to explain the relevant physics. And normally when you understand what's going on well, metaphors and analogies can be almost the truth. You just have to decorate them a little with some sharper equations, and it turns into the truth. And that's really not the case for almost all the metaphors and the analogies that you've heard about the Higgs. They're just horrible. They're absolutely horrible. I did it myself. I mean, in describing this physics, not to fellow scientists perhaps, but to popular audiences. There's all these horrendous, wrong, misleading, terrible analogies, like wandering through molasses, or you can pick them and time how long it'll take me to go into a rage over them, even though I do them myself.
But it's a godlike particle, right?
that of course. I mean, that.
But if you don't send yourself into a rage, that's like immunology.
Right. I was looking. So anyway, what I've started trying to do is do something very dangerous, which is to actually explain exactly what's going on. And I'd like to do that in this talk. And actually, I want to step back a little bit and put the story of the Higgs in a somewhat broader context. People from outside, far outside particle physics, or this part of theoretical physics, might sometimes get the sense that we're just a bunch of people who make shit up. And sometimes that stuff turns out to be true. Who knows if the current ideas are true or not? But you may get the impression that we're just inventing stories, fields, leprechauns, fairies that may or may not be there. Until the experiment comes along, and delivers its verdict. And that's actually very far from the correct impression of what's actually going on, and something which is not well appreciated, which is what I want to spend the first 20 minutes or so telling you about, and then we'll continue that into the story of the Higgs, which is really a natural continuation of this fact. Is that actually we don't know all the laws of nature, for sure. We have an incomplete understanding of things. But what we know already, in particular, the general principles of relativity and quantum mechanics, both of them are absolutely critical. What we know already incredibly strongly constrains what the world can possibly look like at long distances. And we have an incredibly constrained and powerful framework that's basically forced on us by these two principles. In which to operate. And that's the first thing I want to tell you about. But essentially, what we know already gives a tremendous inevitability to almost everything we know about the laws of nature at very long distances, long compared to some truly microscopic scale, much smaller than we've been to experimentally today. And once you appreciate that and appreciate the incredible straitjacket in which we are operating, you'll better be able to appreciate why it was that a huge majority of us, a large majority of theoretical physicists, were completely convinced that Higgs had to exist long before there was a shred of direct experimental evidence for it. Okay? I was not alone in doing this, but I bet a year's salary that the Higgs would be discovered. someone took me up on it. Actually, they sent me a blank check. They said they were so sure the Higgs wouldn't be discovered, but they also thought that I was an honest guy. So that if the Higgs was discovered, I could feel free to fill in $100 plus the mass of the Higgs in GeV and cash it. That's fine for 2 or 3 nice bottles of champagne, which I, in anticipation of this check, splurged on July 4th when the Higgs discovery was actually announced. Alas, the check is still in the mail. Okay, so the talk's going to really have 2 parts, and if there's any time at all, I'll talk about the third, which is really starts getting into the core of the kinds of questions that are being discussed at this workshop. But the first part is to explain why it is that, given what we know about the world, whatever the underlying theory of everything may or may not be, we have a very, very constrained and simple structure that can describe the world at long distances. Secondly, I'll talk about how the Higgs fits into that picture and why it was so inevitable and why we're sure it had to be there. And finally, if I have time, I'll tell you why, nonetheless, it's very mysterious that something as simple as the Higgs is actually responsible for this physics. It's very strange. It brings with it a number of very sharp paradoxes, and I'll talk about some of the possible ways those paradoxes can be resolved and some of the ways in which we're going to be probing these things experimentally in this decade. Okay. So first, and by the way, certainly if you want to read more about this and much more eloquently, I urge all of you who haven't read it to read Steve Weinberg's great popular book, Dreams of the Final Theory, where these things are described more eloquently than I will here. Okay, so first, let's just quickly start with a review of what we know about all the matter and interactions in nature. So we have particles and forces, electrons and protons and neutrons and atoms. The protons and neutrons are made out of quarks. And for a long time we knew that these particles also had interactions, the electromagnetic interaction, the gravitational interaction. In the 20th century we learned about the weak and the strong nuclear forces that operated at much smaller distances. But if I sort of summarize what we've learned that all of these interactions are actually associated with these little stick figures. So we have some interaction between 2 electrons and a photon that's responsible for electromagnetism. An interaction between 2 electrons and a graviton that's responsible for gravity. Then the less familiar interactions, we have an interaction between an electron, something called electron neutrino, and a W particle, which is responsible for the weak interactions. A close cousin of this also, so these things are very close cousins of each other. And we have interactions between quarks and gluons. So what we normally think of as the electromagnetic force, we can think of as 2 electrons coming along and exciting virtually, quantum mechanically, a virtual photon. And this gives the electromagnetic repulsion between electrons. We similarly can have the same thing between the electrons to give the gravitational force between them. And you won't need to understand too much in detail about what these things look like. I'll say a little bit more about the salient parts we'll need in a second. But one thing which is important is that the photon and the graviton are massless particles. And so these forces, even though they dilute as you go to longer and longer distances, are noticeable at longer and longer distances. They give you forces that scale like the inverse square law. The fact that it scales like the inverse square law tells us something important. It tells us that the quantum fluctuations for these massless particles do get smaller as you go to larger and larger distances. And conversely, get larger at smaller distances. But nonetheless, we can still notice them. They just scale like the inverse square law. The reason it took a long, long time in order to see that the weak and the strong interactions look basically the same is that there are differences between these interactions that only show up at very long distances, despite the fact that at short distances they look essentially identical. So the W and Z particles have a mass. Because they're massive, the size of their quantum mechanical fluctuations actually, at long enough distances, gets exponentially small, so we really don't notice these things. It's just not a matter of inverse square law. Their effects are exponentially small. And something more subtle and interesting happens with these guys, which still, the strength of this interaction between quarks and gluons at small enough distances looks more or less the same as everyone else. But at large distances, where large here is distances around 1,000,000 times smaller than the atom, large for a particle physicist, get large enough that they bind the quarks and gluons inside the proton and the neutron, so we don't notice them. But this is a sort of a big accomplishment of 20th century physics that we realize when we go to short distances that all these things essentially look identical. By the same kind of rules, the same kind of basic stick figure interactions. And we get more complicated things. All the more complicated interactions that we can actually get come from just gluing these guys together in various ways. So we can get more complicated processes just by putting these basic stick figure interactions together in a variety of ways. Okay. Now, there is a particular menu of these particles that we've seen. There are particles like electrons, and photons, and gravitons, which are perhaps familiar. Up and down quarks are inside the proton and the neutron, so they may be a little familiar. There are less familiar particles, which are heavier copies of these guys. So there's some particular menu of them. The menu doesn't look tremendously simple. It's not tremendously complicated, but there's some menu of a small number of these particles. But again, importantly, everything boils down to these basic fundamental interactions, and gluing them together in this particular way gives us all the more complicated interactions that we know about. Now, there's one more important thing that I should tell you about particles, which is that particles have an important property, something that labels them, part of their name if you like, which is that they have an intrinsic angular momentum or spin. So an electron can have an intrinsic angular momentum or spin of plus or minus a half in units of Newton's constant. And in principle, we could have intrinsic spin of 0, 1/2, 2 times a half, 3 times a half, and so on. Okay? So we can have integer multiples of a half h bar spins. That's what we can have on general grounds. But then we can ask about what spins actually we see in the elementary particles of nature. The spins we actually see are spin a half for electrons and quarks and so on. For photons, they have spin 1. The W and the Z have spin 1. Gluons have spin 1. All these guys are a half. And the graviton is special. There's only one graviton. We don't have 12 kinds of gravity. There's one graviton, and this has spin 2. Okay. So what we've seen so far, at least until July 3rd, is a menu which has particles of spin 1/2, 1, and 2. This guy is unique. We have a bunch of these. We have a bunch of these. Okay. And the basic interaction are these basic ABC 3-point interactions that we then glue together to make more interesting processes. Okay. So already here, we can ask 2 questions. Well, I mean, there's something which should be puzzling you. Why is it so simple? I told you we have some menu with more and more names of these particles. But why are we so lucky that the basic interactions are just these 3-point interactions, and we can make more complicated ones out of gluing together just these simple ones? It could have been, well, why don't we have basic interactions that involve 12 particles coming together? Well, that's 6 of them coming together in some way. Okay, that's question 1. It could have been, and that would have been a complete disaster for describing nature in any simple way. And yet, that's not what we get. We just get these simple stick figures. So why not these? What? And secondly, why do we have such a tiny menu of spins? We could have had spin 333 halves particles, okay? But we don't. All we have are these 1/2, 1, and 2. And that's it. Okay. Now, the answer turns out really to be quite remarkable. Again, we don't know everything about nature, but we know that we have the principles of quantum mechanics and the principles of relativity. And if we don't want to do violence to these principles, the claim is the following: that quantum mechanics and relativity alone imply that no matter what the underlying theory of everything might be, at long enough distances, nature is guaranteed to be described by A, interactions that are essentially these stick figures, A, B, C, and B, now, let's say you handed a bunch of theoretical physicists who knew relativity and quantum mechanics. You just handed them those principles. You didn't let them peek at what the world looked like. You just hand them those principles and ask them to go and try to construct a consistent reality consistent with those 2 principles without peeking outside. Okay? What they would tell you is first that that's what we'd see. Those are the interactions that we'd have to use to glue things together. And secondly, the possible menu of allowed particles have spins 0, 1/2, 1, 3/2, and 2. Okay? That is the claim. I'll try to explain the claim a little bit. And the explanation of the claim will naturally set us up to understand the importance of the Higgs as well. And actually, the properties of these particles get more and more special as you go to higher and higher spin. For example, spin 2 is just dead unique. It's absolutely unique. There has to be one of them. Its interactions are completely nailed, and that's gravity. So if Einstein didn't exist, if his elevators didn't exist, if all of these Newton didn't exist, but theorists were handed relativity and quantum mechanics, they would discover that there's an absolutely unique way of having a massless spin 2 particle, and they would construct gravity just out of the principles of relativity and quantum mechanics. And these guys are totally, almost unconstrained in the kind of interactions they can have. They have these stick figure interactions still within this class, but they get more and more special as you go along. These guys have to interact in a relatively special way. These guys are quite a bit more special. We'll come back to them. But you can have as many of these as you want, as many of these as you want. For example, you can have at most 8 of these, it turns out. Okay? There's an interesting number, 8. That makes sense. All right? Okay? Now, I'm not going to be able to prove this to you. You do need, 1 year of grad school in particle physics after all to understand some of these things. But I can give you the nature of the argument so you can understand what the logical structure is. Okay? And again, once we understand this, we can move on to talk about the Higgs. All right. So we're first going to address the question of why it's only these simple stick figure interactions. Okay? And believe it or not, to do this, we're going to think about something extremely basic, which is units. Okay? We're going to spend some time talking about units. I don't know about you, but units were the bane of my existence in physics high school. I could never keep them all straight. They're all tremendous pain to remember what mu naught and epsilon naught and all these terrible things were. And there's a good reason why they're confusing. It's because the way we normally teach units are completely human constructs. They're not related to nature at all. Of course, there's nothing that actually has units. Everything we measure is really dimensionless. When we say so-and-so person is 2 meters tall, we mean that there used to be a bar in Paris that we called 1 meter. And if we took that bar and lay it down, end to end twice, we would reconstruct the height of the person. Now that's great. Human beings invented these measures for good reasons. But if you're trying to describe to a friend in the Andromeda galaxy how tall this person is, it would do them no good to say that if you went to Paris and got this bar and laid it end to end, they don't want to come to Paris. Okay? But fortunately, there are much better units that we can choose. First of all, nature has both relativity and quantum mechanics. So we like to use units where the Planck constant and the speed of light are set equal to 1. What does that mean? Well, you're probably most familiar with it, units, at least tacitly, where you set c equal to 1. It's because a position and a time are related through a velocity. So when you work in units where c equals 1, you mean when you say 1 light second, that's equivalent to 3 times 10 to the 10 centimeters. So you can move back and forth between a distance and a time using the speed of light. So we don't have to have 2 different units for time and distance. We can just use one of them. Let's say distance, and it can be a stand-in for time as well. Now, something that you also probably remember is that the uncertainty principle tells you that uncertainties in energy times uncertainties in time is the Planck constant. So just by units, that tells you an energy and a time are related like this. So you see that we had distance, time. Now, using Planck's constant, I can convert everything also in energy to a time or a distance, and in this way, I can take any quantity that you're familiar with and relate it to 1 unit. Okay, it's very convenient. So, the unit that we tend to use in particle physics is a unit of energy. I'll tell you the conversions in a second. The mass of the proton is around, not exactly, but is around 1 giga-electron volt, which is lucky for us. I guess giga wasn't a person, but Mr. Volt couldn't have known. Mr. Volt couldn't have known this, but it's very convenient for us that this is approximately true. So we use units of GeV, and we can convert everything to those units. So, for example, the size of a proton is around, well, as you expect, it's 1 over, to get a length, it's 1 over a time, which is a distance. So size of a proton is 1 over a GeV. And we can translate that to ordinary distances. It's around 10 to the minus 14 centimeters. So 1 over a GeV is around 10 to the minus 14 centimeters. 1 over a GeV is around 10 to the minus 24 seconds. Okay? So we could tell the person in the Andromeda galaxy that so-and-so person is 10 to the 16th inverse GeV tall, and that would be meaningful to them because they would say if they put 10 to the 16 protons end to end, they would make the person. Okay? If you're very lucky, this lecture will be 10 to the 27th inverse GeV long. All right. The energy of the LHC, the protons that are being collided at the LHC, the center of mass energy is 7,000 GeV. That gives you an idea. It's 7,000 times the typical rest mass energy of the proton, and so on. Okay, so these are great units. They're natural units. They're called natural units for obvious reasons. They're now units that have to do with nature, not to do with what human beings decided to put in some jar in Paris 100 years ago, whenever it was. Okay. Now, with these units, we immediately learn some rather profound things. Okay? Let's go back and think about things that you're very familiar with. Like, let's look at the force between 2 electrons. Or let me, better yet, talk about the potential energy between 2 electrons, which, if you remember, is a formula that has some e squared over 4 pi. Normally there's some mu naughts and epsilon naughts, but there's just some constant. And the potential goes like 1 over r. The force goes like 1 over r squared. Okay? If we do the same thing gravitationally, we would instead get the Newton constant times the mass of 1 electron times the mass of the other electron, 1 over r. And now we learn something remarkable. Notice that 1 over r already has units of energy. So this e squared over 4 pi is a dimensionless number. E squared over 4 pi, this is the fine structure constant, it's around 1 over 137, is just a small dimensionless number. Okay? That's cool. It tells us that there's an intrinsically small number associated with electromagnetism. Electromagnetism is weak. It's intrinsically weak. There's a sense in which it's intrinsically weak. Its strength is a small number. What about gravity? You see, it can't be the same because it's g Newton times the mass squared, which is dimensionless. So g Newton has to have units of 1 over mass squared or length squared. And if we work it out, g Newton in these units is 10 to the minus 33 centimeters squared. This is the famous Planck length squared. Okay? And g Newton is not a small number or a big number. It's dimensionful. So there's no invariant sense in which gravity is weak or strong. It's weak at very, very large distances compared to 10 to the minus 33 centimeters, and it's strong at short distances, or starts getting strong as you start approaching this tiny length scale around the Planck length. Okay? Okay, so there's this important difference between these interactions. Now there's one more characteristic that's associated with these interaction strengths. And that has to do with quantum mechanics. So the world is quantum mechanical. So damn it, when you collide two particles in exactly the same configuration over and over and over again, the same thing doesn't happen time after time. Something different happens every time. Sometimes they come out like that. Sometimes they come out like that. Sometimes they come out like that. Okay? And all we can do is predict the probabilities for those things to happen. Okay? And these numbers, so these pictures give us a probability amplitude that we then have to square or mod square to get the actual probability. So what this really means is if you take two electrons, you collide them at incredibly high energies, and you ask, what is the probability that they come out at bigger than 45 degrees? Okay, so that something big happens to them. Okay? The answer for that probability is that it's this small number, alpha, squared. Okay? So not much happens typically when you collide them. Okay? It has a small probability for them, for something exciting to happen, for them to come off at a big angle. Okay? And you see, it's very nice that that number is small. It's always small. So probabilities all got to add up to 1. So if the probability for something happening is small, that means the probability for nothing happening is big, but everything is consistent. Okay? Now, the mystery of gravity, one of many mysteries associated with gravity, we can also see here. What does the probability look like here if we're talking about gravitational interactions? So if there's some energy here, that probability cannot be, so if the probability was alpha squared for E and M, which is small, but the probability is g Newton energy squared for gravity, which is minuscule when energy is small compared to the Planck length of Planck scale, but start becoming 1, and in fact bigger than 1 if you naively extrapolate to energies above the Planck scale. Okay? So that's one of many ways of saying that something is going wrong with gravity and quantum mechanics. You just take them, and the most basic feature of interpreting something as a probability, that the probability should add up to 1, starts being violated when energies start becoming Planckian. Of course, probabilities won't actually get bigger than 1, but it tells us we're missing some important part of the physics that has to start kicking in at around this energy scale. And we get an estimate for that, what that energy scale is, around the Planck scale again. Okay. Now, so now we can get to understanding why the world is so simple in 2 easy steps. So let's first try to, so note that it's these interactions that we talked about. It's these ones that were associated with the usual electromagnetic interaction, for example, that had these dimensionless couplings, dimensionless strength of the interactions. Okay? We can immediately understand then why it is that we can't have these horrendously complicated interactions. Okay? Well, we could have them. They might even be there, but they'd be utterly irrelevant and not noticeable at low energies or at long distances. So why is that? You see, if this interaction is actually going to happen, just like in this case, you know, when we glue two of these guys together to make this interaction, remember, we get an interaction that falls off like the inverse square law. That means that the size of the quantum fluctuations here are getting smaller and smaller as you go to larger and larger distances. Conversely, the other way around as we go to shorter distances. But if we're going to have two guys in, making a whole bunch of guys out, you have to produce out of the vacuum, and they have to fluctuate out more and more and more of these guys. Each one of them costs, right? Even making any fluctuation at all costs. Even one of them costs. If you have 2, 3, 4 of them, they cost more and more and more. And that means that the strength of that interaction cannot be dimensionless. It has to depend on energy scale. It has to grow as you go to higher energies. It has to shrink as you go to lower energies. And you know, this is a kind of a deep argument, even though it's only dimensional analysis. For example, it depends on the number of dimensions of space we're in. Okay? If you made the same argument in one dimension of space and one of time, you wouldn't reach the same conclusion. For certain kinds of interaction, you could have infinitely many of them. Okay? But because we're in 4 dimensions, things go like the inverse square law and so on and so forth, that we surmised already from there, all of these interactions that have more and more things coming out, these interactions cannot be dimensionless. They have to have some small length in front of them to some power. Okay? And therefore, they're invisible at long distances. The world may have them at very short distances, but they're irrelevant for talking about physics at long distances. So this is a very deep idea that nature at long distances is described by effective theories. And the only dimensionless couplings that we can possibly have turn out to be, as you would expect, these stick figure ABC interactions. Tiny caveats I don't want to spend time explaining. Okay, but essentially this. Now you might say, well, wait a minute, but what about gravity? Gravity, why are we talking about gravity if we're not talking about all the other ones? Gravity is very, very special. The only reason we notice gravity, it is tiny, it is minuscule. The only reason we notice it is it's universal. It adds up, it doesn't cancel out when you put positive and negative charges together. And minuscule and tiny as it is, it's the only relevant thing that remains at very, very long distances. But anything else that's not gravity, you'll never know that it's there. Okay? It's irrelevant for building any picture of physics at accessible energies. Okay, that's part 1. Part two is why is it that the only menu of spins we have are these very, very simple ones? Well, let's see how far we could get trying to determine what all these interactions look like just from first principles. You might try to think that the first thing we should talk about is the most basic collision process at all. 2 particles come in, 2 particles go out. That's the most basic thing we could talk about of all. And that's already a pretty complicated thing. Imagine you have 2 particles in, so we can always go to a frame where they have equal and opposite momenta. Okay? So we'll call the energies they have in that frame E, the center of mass energy. And some stuff can come out, and it can come out at some angle relative to how they went in. So we can ask, what is the probability amplitude for this process? The world is quantum mechanical. And this could be a complicated function of the energy and the angle. And that's all I can say without knowing anything else. So it doesn't seem, it still seems like that could be arbitrarily complicated. But fortunately, these Carnot processes are not the most basic ones that we have a chance of seeing at long distances. The ones we should talk about are these guys. Let's talk about these guys. We normally don't talk about them so much. Well, I should have said something here. Since we're imagining that there's some underlying theory of very short distances, short distances is very high energies, it's a good first approximation to neglect the masses of all the particles. So we're going to imagine that all the particles are massless. The story that Higgs is going to have everything to do with putting the mass back in and seeing how much of a mistake we made in taking that approximation. But clearly, at least just as far as any kinematics is concerned, obviously if the energy is way, way higher than mc squared, as far as any processes involving these guys are concerned, we should be able to neglect the masses. So let's do that. If we neglect the masses, the notion of spin becomes a little more interesting. Let's say we just have massless particles that are flying around. Imagine that it was a massive particle for a second. Okay? Let's say the massive particle has some spin. Let's say it's a particle that has spin 1. So if it's massive, we can always go to a frame of reference where it's at rest. And then we see that maybe it's pointing in the z direction. That if I tilt my head, I can think it's pointing in the x direction. If I tilt my head again, it's pointing in the y direction. So it has all 3 spin degrees of freedom that it should have for spin 1 particle. But if it's massless, we can't do that. If it's massless, there's no frame of reference where this guy's at rest. And so all we can talk about as far as its intrinsic angular momentum is concerned is what its spin is in the direction of motion. So it would be spinning in the direction of motion or opposite to the direction of motion. And this is, we'll still call it spin, it's sometimes called helicity. Okay? And there's only 2. So if we have a massless spin 1 particle, it just has 2 helicities, in the direction or opposite to its direction of motion. Okay? All right, so now we're ready to start looking at this basic ABC interaction. So here we have A and B and C. So you first think, well, we can have A decaying to B and C. But if these particles are massless, that can't happen the way I've drawn it. Just think about what it would take to conserve energy and momentum. If you want to conserve energy and momentum, you can't just have a massless particle decay into 2 massless particles, one that goes that way and one that goes that way. Okay? The only thing you can have is to have it break up into 2 guys that are moving in exactly the same direction. Okay? So that's interesting. There's no analog of the angle that we had in this case. That complexity is gone. Okay? Now here we also have the analog of the energy. But you see, there's also no analog of energy that we can have here. The reason is, depending on the frame of reference in which I go, the energy of A changes. Okay? So if this amplitude is, again, now we're talking about amplitudes is quantum mechanics. Relativity we're now also putting in. Okay? Then what can this amplitude possibly depend on? Nothing. It can't depend on energy and it can't depend on angle. In fact, the only things it can possibly depend on are the spins of the particles, or the helicities, and that's it. So this is remarkable. Up to an overall strength, up to its strength, these ABC interactions are nailed, are completely nailed by relativity and quantum mechanics. Nothing you can do about it. Now, so far, I could have particles of spin 17 and 333 halves just as well as 0, 1, and 2. But now comes the second important ingredient. And I think I actually gave a Blackboard talk on this kind of subject at greater length a number of years ago. So if anyone is interested in seeing more, I think I probably explained this in more detail there.
So what's the dimension there?
Sorry?
Function is dimension.
Yeah, so I'm not telling you everything. You see, the amplitude for this process is actually 0, okay, which is why we normally don't talk about it. But it's 0 only because we demand that the momenta are real momenta. If the momentum is a complex momentum, it's not 0, but the rest of the argument goes through exactly the same way, and it's nailed, and the dimensions are nailed as well. Okay, so there's an overall coefficient that depends on the. But it's just a number. It might be dimensional, okay? But it's just a number. Okay. Now there's a second basic principle. Now coming back to this process where 2 go in and 2 go out. The second basic principle is that, as we move these energies around of all these particles, typically this probability will be small, like we saw. It will be a small number, right? But every now and then it should become large, and it should become large when something that we normally think of as a virtual particle becomes a real particle propagating in the intermediate state. It's just a phenomenon of resonance. Okay? These amplitudes should become large when it has a resonance. And the resonance happens when it's possible for two of these guys to combine into a massless particle. When that happens, furthermore, this thing had better turn into the product of two pieces, the sort of amplitude that it was made, propagated along distances, and it decayed on the other side. So here we're again putting in the principles of relativity and quantum mechanics that tell us the kind of the places where it could get big and how it has to behave in the neighborhood of where it gets big. We know everything about that interaction from the argument I just told you, so these things are just God-given to us. And this is where you need a year of grad school. Okay? Okay? Actually, the argument fits on one page. It's a very, very simple argument. You don't really need a year of grad school. You could explain this to a very smart high school student. But you see, it depends on what the spins are through the fact that this depends on what the spins are. Okay? And you find amazingly that it's almost always impossible to make this happen. Okay? Impossible to come up with a well-defined scattering like that, which gets big where it should and in the way it should. And that there's only a tiny number of exceptions which are possible. And those are the ones which are spins 0, 1/2, 1, 3/2, and 2. Okay? And actually, you learn everything about them. For example, you learn that the spin 2 is completely dead unique, as I said, and it's got to be gravity. You learn, if we talk about spin 1 particles, you'll notice nowhere in this discussion have I said the word Lagrangian, nowhere have I said anything about gauge symmetries or fancy words like that. Here we're just seeing what's forced on us by relativity and quantum mechanics, and what we get is what we get. But for instance, if we have more than one spin 1 particle, if we label them by an index A, which runs from 1 through however many there are, so we have A, B, C, then the strength of this interaction I can call something. I can call F, A, B, C. It just depends on what A, B, and C are. And these requirements force those F, A, B, C's to be the structure constants of a Lie algebra. So it tells you that there is a gauge symmetry, or that kind of structure exists, even without saying the word gauge symmetry, which doesn't actually exist in this way of thinking about this. Or if you have other particles, there are a bunch of these guys, let's say spin 1/2 particles, and they can interact with these guys. Then the strength of this interaction you could call just something that depends on A and depends on I and J. And these guys have to be the generators of a Lie algebra. Okay? So these things are just nailed, forced on you. Nothing you can do about it. 3/2 is interesting. We'll come back to it. We probably won't have time to come back to it. So 1, you can have a bunch of them. They can have these kind of self-interactions. They're very constrained, but not completely nailed. 2 is nailed, is just GR. And 1/2 and 0 are more promiscuous. Okay, they can interact with each other however they like. Okay, so that's it. Independent of any language or formalism or picture that particles are really excitations of the field and all of this stuff, most of which are words, most of which actually don't have actual invariant content, okay? We've learned that whatever the laws of nature are at short distances, at long enough distances, they must be described in this horrendously constrained framework. Only those particles, very special kinds of interactions. And we can discover all the things that are actually out there in nature by pure thought, okay? Just from consistency with the principles of relativity and quantum mechanics. Now, it's fascinating that what we've actually seen is this guy, until July 3rd, that guy, and that guy. Okay? So there are two things that it seemed like nature could be making use of that it was not making use of. 0 and 3/2. All right? All right. So now let me turn to the story of the Higgs. Which, as we'll see, is going to start showing that we're going to make use of more things that we're allowed to use. All right. So remember, everything that we talked about here was in some approximation where we think of all the particles as massless. Okay? But actually, we have massive particles. As I mentioned before, the W and the Z particles, which are responsible for the weak interactions. A neutron in outer space decays to a proton, electron, and an anti-electron neutrino in around 15 minutes. So 15 minutes is a humongous time scale compared to all the atomic scales of nuclear and particle physics and so on, which is why this was called the weak interaction a long, long time ago. Okay? So some incredibly feeble interaction that over a 50-minute time scale caused neutrons to a decay. We now understand that its feebleness is just reflecting the fact that it's associated with just a stick figure like the ones that we talked about. If I attach it to an up and a down port here, this is what makes a neutron decay to a proton, electron, and an anti-electron neutrino. But it's related to the fact that this W particle has a mass. The mass of the W is around, let's call it 100 giga-electron volt. So again, its size is around, the typical length scale is around 100 times smaller than the atomic nucleus, which was 10 to the minus 14 centimeters, or 1 over a GeV.
So I have a question.
Yes.
In what sense we know that the graviton exists? Then in what sense you say that we saw spin-2 particles? Just because we saw gravitational interactions?
We've seen gravitational interactions, we've seen gravitational waves, we haven't seen individual gravitons yet, it's true. We probably won't ever see. Right. Right. But from this point of view, we're just taking the principles, pure thought, and it predicts that these things can exist at long distances, and almost all of them do exist. All right. Now remember that this guy's a spin 1 particle, and we said that, well, if we're imagining its interactions at very, very high energies, we should be able to neglect the mass. And that's true purely as far as kinematics is concerned. We can neglect its mass. Okay? But there's a huge difference between massless and massive that we already talked about. This massive spin 1 particle has 3 ways it can spin. It has 3 degrees of freedom because you can boost to a reference frame where it's at rest and then see all 3 of them. But the massive spin 1 particle has 2 degrees of freedom. So our first problem is that 3 is not equal to 2. If we want to imagine we're describing these things at very high energies or short distances, there's 1 extra degree of freedom that we have to talk about that we're not taking account in our previous picture. And this degree of freedom is actually dangerous. Remember, we were saying before that all of these interactions that involve spin 1/2 and spin 1 particles, they all have these nice dimensionless interaction strengths. So I didn't tell you, but all of these dimensionless interaction strengths for all these stick figures that we talked about, electrons and photons, that strength is around the square root of 1 over 137. But all of them are kind of comparable. Like this guy is around the square root of a 60th. This guy, between 2 quarks and gluon, is around the square root of a 10th. Okay? So they're all roughly comparable to each other. So we talk a lot and speculate about what some theories might be that would unify all the forces. But in a really sharp and wonderful sense, we are 95% of the way there already, because we've learned to talk about all the interactions on an essentially identical framework. And as we've seen, that framework isn't something that we make up. It's forced down our throats by relativity and quantum mechanics. Okay? All we have, the only freedoms we have in this picture, are dialing the strength of these interaction strengths. Once you give the menu of the particles, all you have, instead of a continuous infinity of parameters to describe nature, we have this tiny small number of parameters, 19 or 26 in our current picture of the world, but 19 or 26 is smaller than infinity to high powers. Okay, and they're all roughly comparable to each other, and they're all small. Okay, so that's good. So we have this nice weakly interacting picture for all of these particles at high energies. And you might think that would tell you that if you consider some process, just like we talked about, let's say we have W's coming along, banging into each other. So we have W's in, W's out. we could estimate what is the probability for these interactions to happen. And the estimate that we would get is, well, the probability would be, something like this number, one of these alphas, it doesn't matter which one, squared, something like that. And you'd be wrong. You'd be wrong because there is something we were not taking into account in our previous picture was when we're talking about all these interactions, we assume we were talking about the massless W particle. Okay? But when it's massive, it has one extra degree of freedom. Now, imagine you have the W sitting here at rest to spin one particle, and it could spin in this way, that way, or that way. Okay? Now, I'll say something loosely. You can complain about it, and then I'll say something more correct in a second. But just so you get the idea loosely, there is some amplitude to find the W here, here, and there. Okay? Now, let's say you boost the W so it's traveling very fast in that direction. Okay? By the normal principles of relativity, you're used to the fact that things that are sort of measured orthogonal to the direction of the boost don't change. Okay? So these amplitudes are the same. But you're also used to the ideas of length contraction and time dilation. Okay? And as I said, loosely, the amplitude, to find it, spinning in the direction that it's moving in, grows with energy. Okay? Now, these guys, which are spinning orthogonal to the direction it's moving in, those are just the helicities that we're talking about before. Not just spinning this way or it's spinning that way. Okay? So when we draw these pictures, we're sort of tacitly assuming that the sort of amplitude to find the W's in the states that they're scattering are just numbers of or 1, and that all that matters are the strength of these interactions. And if we do that, we get this estimate, and it's correct. But the new thing is that actually the amplitude to find it in this new state, the one that's spinning, where it's spinning in the direction it's moving in, grows itself with energy. So that instead of getting something that's just this small number squared times 1, you get the small number squared times something that grows with energy, like the energy divided by the mass of the W, as it turns out, squared. So that tells us something without that the situation then becomes exactly the same morally as a problem we had with putting together quantum mechanics and gravity. Okay? We just take these particles as handed to us. In that case, it's gravitons. We look at what the probability for them interacting with each other is, and we find that that probability grows with energy until somewhere it becomes 1. Before it gets there, something new has got to happen. Okay? In that case, in the previous case, that happened at around the Planck length. In this case, it's happening at an energy scale that's not quite the mass of the W, because this coupling is small, but only a little bit higher than the mass of the W. And it turns out, just numerically, it's an energy of around 1200 GeV. Okay? So, we just take massive W's and Z's, we collide them together, and we learn something without anything else, that something new has got to happen before 1200 GeV, in just the same sense that something new has got to happen beneath the Planck scale to rescue the difficulties with quantum mechanics and gravity. Here it's just quantum mechanics and W's and Z's. So you might have thought naively, from everything I told you, you might have thought naively that the picture was, here you go to higher energies, here's the Planck energy, and up here there'll be monsters. And here we are around 100 GeV, and it's smooth sailing all the way up here with the particles that we've seen. But in fact, the real picture was there's still monsters up there, okay? But somewhere much closer by, we have to have new particles, or something new happening before that. Okay? So this is around the W's. Anyone who's interested, I can give you the more responsible version of this argument after the talk. What I said is obviously not exactly correct, but it's close enough. Okay. All right, so that was the state of affairs through to the, I'm not going to be much longer. That was the state of the affairs through to the late 80s, I would say. And I'm being a little ahistorical here. Notice I haven't anywhere said the word symmetry breaking, Higgs mechanism. I haven't drawn a Mexican hat potential with things rolling down the sides and so on and so forth. Those things aren't wrong. They're not as bad as molasses. Molasses is just crap and wrong. Okay? Those things are not wrong, but they're not right either. Okay? They're one way of talking about things. They're not the only way of talking about things. There are other ways of talking about things, and actually, as we've learned, the other ways of talking about things are sometimes sort of the more invariant ways of talking about things survive, even as all the words surrounding the older ways we had of talking about things change. And so I'm deliberately not talking about it in the usual language, partially because I want you to see how much everything is forced on us, and we can't do anything about it. Okay? It isn't that we choose a language and someone else could choose some different language or a different formalism or nothing, right? This is just physical facts about the particles we have, how they interact, and what's forced on us. All right, so now, what might you have imagined would happen here? Okay? Well, what many people imagine, a lot like actually what people imagine happens in the case of gravity in some ways. Okay? What many people would have imagined is that, so what's going wrong? What's going wrong is that these longitudinal components of the W's are getting more and more strongly interacting with each other as you go to high energies. I should have said that there's a couple of massive particles. There's W's that can interact with each other. There's also top quarks, which are very heavy particles, comparable in mass to the W, a little heavier, that can also scatter against these longitudinal components of W's. And it's all of these interactions are the ones that are getting dangerously large, and something new has got to happen by around 1,000 GeV. Okay. So what might you have thought would have happened? You might have thought, well, these longitudinal components, they just become strongly interacting mush at very high energies, and they turn into something radically different. Okay? That radically different could be maybe they're bound states of underlying spin-half particles. Now, notice everything that we did previous to this is not useless. It tells us, if we're going to give some description for what's going on at very short distances, it tells us what it has to look like. It has to involve spin half, spin one, the whole machinery that we talked about. It's got to be what it turns into at very short distances. Okay? So you might have thought that that's what would have happened. Okay? That these longitudinal components of the W's just become mush as you go to very short distances. Now, and you also might have thought that, well, what do we actually have to do? Someday we have to actually build an accelerator that collides these W's into each other at very, very high energies and see what that mush is and see what it turns into. And that was really the raison d'etre of the SSC. Okay? The SSC was built with the energies that it had, with the whole vision to make sure that these interactions of W's, longitudinal W's, would be correctly captured and studied. Okay? But some great theorists, some of them were supposed to be at this meeting, but which I don't see here, decided to take matters into their own hands and not wait decades for this machine to be built. Because you see, there's something that you can do and that you can calculate ahead of time. Hardly with not very much model dependence. All you have to do is assume that nothing new is happening to around 1,000 GeV, and then you can start calculating corrections to properties of the W and the Z. So in here you could have running around these longitudinal components of the W and the Z. Okay. Here's the Z particle that was this cousin of the W particle. Okay, and this would, if you just estimated given what we know about the alphas, and if you're as proficient as these people doing the calculations, you see that this would have given rise to percent level modifications in the couplings of the Z particle to ordinary matter. So here's ordinary matter, electrons, muons, quarks, and so on. Okay? So these people actually did the calculation, and the answer was that. It was around percent level, and the percent is sort of what you'd expect from that alpha. Okay? Actually, alpha is more like 10 to the minus 3, And there's an important logarithm in this answer. For technical reasons, the presence of the logarithm is what actually makes you reliably be able to calculate it. If you didn't have the log, you might not think that you knew how to calculate everything, but the log lets you actually compute it. And the log is between around 1,000 GeV to 100 GeV, and it's big enough to enhance these per mil level effects to around a percent level effect. Okay? So these theorists did this calculation. There's actually two important quantities. Now we know that there's more, but there's still essentially two important quantities I won't tell you what they are exactly, but they're essentially this. Okay, one of them is actually telling you about the coupling of the Z to electrons and muons. The other one is telling you something about the mass ratio of the W and the Z. Both of them would have been expected in this picture that it's just mush at 1,000 GeV. Both of them would have expected to give you percent level deviations compared to the leading order couplings. Then some intrepid experimentalists went off and measured them. And you could measure them to this sort of per mil accuracy by making roughly, 5 million of these Z's. Maybe more, I forget. Many millions of Z's. So many millions of Z's were made. These couplings were measured. I won't draw the plot. And remarkably, these percent level effects were not seen. In fact, they were nailed to be at per mil level. Okay? Now, all of this might sound like it's very detailed, right? And we're not talking about humongous differences here. It's a percent versus per mil. But this is the typical way we work in this part of physics. You take the theories you have as seriously as you possibly can, and you take every prediction they make seriously, and you confront them with experiment. In this case, basically independent of models, you see that there's a contribution that you can just calculate to these precision observables. That's sort of 10 times too big compared to what was seen experimentally. Okay? And that meant that the most conservative possibility of all, that these longitudinal W's just turn into mush at high energies. And when I say it's conservative, it's because elsewhere in physics where this kind of thing occurs, it's always been that possibility that is realized. Okay? That's not what seems to be going on with the physics that we have in the vacuum of our universe. So that means that here, not only is this picture wrong, this picture is also wrong. Something new was needed much earlier, right above our head at around 100 GeV, in order not to make these corrections too large. Okay? And that's why we knew since the early 1990s that there had to be some new particle. We couldn't say precisely where it is because it depended on the logarithm, but we knew it had to be. But it's amazing that we could get this far with the logarithm. Okay? We knew that we had to have a particle, somewhere between 50 GeV and 200 GeV or so. Okay? Without even saying what it is, I still haven't said the word Higgs mechanism. In fact, I probably won't say it at all. Okay? Without knowing anything in detail, something new had to show up a lot earlier than the original argument told us it absolutely needed to be. All right, so let's wrap up. Now we can finish very quickly. I have to say, this all happened right as I entered graduate school. And it had a very profound impact on me personally. This is a big reason I went into particle physics. Because I was not at all convinced that the vacuum of our universe is so particularly interesting, or more interesting than what condensed matter physicists do in the lab all the time. What condensed matter physicists do in the lab all the time is fantastically interesting. They have zillions of different theories that they get to play with. And here we are stuck dealing with one theory, the vacuum of our universe, and it's incredibly difficult and expensive to probe it. So if it's just peeling back one layer of the onion after another, you might as well do it somewhere you can have a lot more fun and play with tons of different scenarios at the same time. This fact is really surprising. This fact already back then is incredibly surprising and suggests there's something new and interesting about the physics of the weak scale, unlike what we've seen before. Not like peeling back one more layer of the onion, but something actually qualitatively new. It also tells us that unlike the previous picture, we're not imagining that these interactions get really strong and then turn into mush. The interactions have got to stay weak. Okay, so whatever's going on, these W's are interacting with each other. Something has got to come in so that these growing amplitudes don't actually grow, and they stay weak. All right, so now we're almost done. So the usual stuff comes from interactions like this. As we said, gluing together these basic ABC type interactions. But this was no good, right? This is giving us still something, when these are longitudinal W's, this is giving us something that grows with energy. So something new has got to come in early. Because it's early, because all these interactions are small, we have to be able to describe it within the rubric that we talked about. There's got to be some particle, it has to have some interactions, these ABC type interactions with these guys. So we have to have some mystery particle X. This X, if it's incredibly heavy, is irrelevant. But if it's light enough in this neighborhood, it has a job to do. And its job is to cancel these rapidly growing amplitudes for the W and the Z. Similarly, I told you we have interactions with the W's and top quarks. And so there has to be something X as well, some collection of X's or whatever. Also, it's got to do the same thing. That's to interact with top quarks. X has a job to do. Okay? We can determine what its properties and interactions are from the requirement that it actually does its job, which is to rescue these humongously growing amplitudes. All right, who could X be? Could it be spin 3, 4, 5? No way. Those are all inconsistent. Could it be spin 2? No way. Tiny caveats to everything I'm saying. Okay, but what I'm saying is 95% correct, 98% correct. Okay? Could it be spin 2? No way. Spin 2 is unique. It's the graviton. Could it be spin 1? Oh, could be spin 1. It could be spin 1, although we then have a funny Russian doll structure, right? Because we're trying to make sense of the interactions of of these massive spin 1 particles, and to rescue it, we have to introduce a new massive spin 1 particle. Well, then what rescues that guy's own private problems? Okay? So you can imagine doing it, but it's clearly complicated. Okay? So it's not ruled out, it's not logically ruled out, but it doesn't smell right from the get-go. Okay? So we're left with one last possibility. It could be spin 0. And when X is spin 0, it's called the Higgs. But I went through the song and dance. I'll just really be 3 minutes here, Lars. I went through the song and dance so you can now learn why we're so completely confident in all of its properties ahead of time, everything except its mass. And even this mass we knew was between 50 and around 200 times the mass of the proton. Why were we so confident? It's because, look, it has to have these interactions with W's, these interactions with top quarks, and so these are nailed from the job that it does. Okay? I should also say that this Higgs particle, this X, together with the longitudinal components of the W and the Z, make up a total of 4 particles. And when you go to very high energies, where now we can neglect the masses because everything is hunky-dory, this Higgs particle, together with the other longitudinal components, becomes one effective particle that has the kind of allowed interactions it can have with the W and the Z and everything else consistent with the first analysis that we talked about. Okay? But even without saying that, and that is a language where it would start becoming appropriate to use the word symmetry breaking and so on, but we don't need to use that language if we don't want. It's just a language. It doesn't have any actual content. But these interactions are nailed. So now let's finally talk about how the Higgs is produced at the LHC. You see, the Higgs has these big couplings to W's and to tops, and naively on the face of it, inside 2 protons, there are not too many W's and there are not too many tops. So how are you going to make the Higgs? Well, here we have a proton. See, here we have a proton. The proton, there's naively 2 up quarks and a down quark here, 2 up quarks and a down quark here. Actually, there's zillions of more quark and antiquarks inside, and there's gluons all over the place, binding them together. The proton is a big, messy bag of particles around 10 to the minus 14 centimeters big. But what we're interested in are the head-on collisions between these point-like entities. And so what can happen is you can have a gluon come out of one proton and a gluon come out of another proton. Now, they can produce out of a vacuum. The top quark is a colored particle, has a strong interaction, so we can produce a top quark out of the vacuum. And now the top quark has a big coupling to the Higgs. And it's nailed. We know everything about it from its job. So that's how the Higgs is produced. In this very indirect, highly quantum mechanical way. This is how the Higgs is produced out of the proton. Okay? So we can in principle calculate exactly the rate at which it's produced. Beautiful. Now, after all these years of planning and now running at the LHC, guess how many Higgses we've made this year? We've made maybe 500,000 Higgses. Okay? That's great. But unfortunately, they don't come out wearing a name tag saying, I'm a Higgs. Okay? And actually, the vast majority of time, what these Higgses do is they decay to the heaviest particle that they can. In this case, they want to decay to a pair of bottom quarks. Another set of quarks that probably most of you haven't heard of. Okay? But they do this like 99.9% of the time. So that's fantastic. We spent all this effort, all this money, all these 6,000 people working to produce 500,000 Higgses. 99.9% of them decay to bottom quark pairs. And unfortunately, we have billions of bottom quarks produced from ordinary strong interaction processes all the time. So this little extra bump of 500,000 of them is not helping much. So what you actually have to do is wait for the Higgs to decay in a much rarer way, but which is much more visible. And that it does by, it's a similar quantum mechanical process there. It turns out to be dominated by having W's virtually produced out of the vacuum, and now producing photons. These are charged particles. Once again, this interaction strength has nothing to do with theory or love of the model or anything. It's nailed by the job it has to do. Okay? So the dominant way it's produced is nailed. The dominant way it decays that we can see is nailed, which is why the only thing that's uncertain is the mass. But everything else we know ahead of time.
Okay, so Nima, I'm going to ask you to write down the mass.
Yeah, so the mass of the Higgs is around 125 GeV, now that it's been seen. Okay? And it's seen in this way. Still, there are 50 to 100 times more photons produced from ordinary processes than from this particular process. But the hope you have for seeing this is that all of these photons, the ones that come from the Higgs, if you add up their energies and their momenta, they should reconstruct the momentum, the energy and the momentum of a moving Higgs. And the rest of them should be sort of randomly spread. So this is a sort of plot that you've probably all seen. There's a sort of big background with a little blip here corresponding to the Higgs. And the blip is there because of the reason I said. The background is all spread out, but what should come from the Higgs all comes from one spot. So we didn't know exactly where it was, but it was more or less in the middle of the window of where we expected it to be. Okay. So this is so I'll just end by saying that so this is all old physics. I'm sort of saying it from a somewhat different perspective. But I think I wanted to illustrate the real power we now have in our understanding of the world. Okay? So it's not a question of choosing this kind of language or that kind of formalism. We know so much about the world that most of its properties are just dictated to us ahead of time. And we're also in the interesting position, however, that what we see in nature does not seem to exhaust all the possibilities. Okay? So this is what, from the top down, we actually see, what we decided that we can actually have. What we'd seen before the Higgs was this guy, and that guy. We went through this entire analysis and we're more or less led by the nose to being forced to posit the existence of that one. You see, that's a very brave proposal. No one had ever seen one of these things ever before. And that's why the Higgs is special. It's not a random other particle. We've seen, gobs of these other guys, but this is the first one of these elementary spin zero particles that we've seen. Okay? Nature could do it. Theoretically, we understand that it's within the spectrum of possibilities, and that's why we're in an interesting situation when we have puzzles that we have to address to see if it's possible to do within the world of possibilities that we know is theoretically consistent. It's a great proposal to say that it should be there, nothing like it had been seen before in physics, and it's there. And it's there basically with the properties that we knew we'd have to have ahead of time. Okay? So that's remarkable.
Deciding whether we should take questions. Sure, cascade. I guess what I'd encourage everybody to do is, let's have a few questions.
Are we sure it's spin zero?
Experimentally, not quite yet, but very close, though. It's getting very close now. Yeah.
So one comment and one question. The comment is that when you say that solid state is more interesting, have gazillion of theories, the right thing to say is that there is gazillion of effective theory. We only have one fundamental theory.
Of course.
And energy seems to be opposite. You only have one effective theory, but have gazillion of fundamental theory that you can postulate. The question is what happens to the mass of the fermions?
Yes. So in this language, we saw it in the case of the top quark already. You have to have some interaction between this particle X and every particle that has all the fermions that have a mass. And the interaction strength is proportional to the mass of the fermion. But, this is describing things sort of building up from the bottom up. From the top down, where we can neglect the masses. You see, it's completely consistent. Everything I said in the first part of the talk is totally correct. But you have to remember that if you want to get this massive W at the bottom, you have to have some extra stuff at the top. Okay? Because you have this one extra degree of freedom that corresponds to the longitudinal component of the W. So if we just start from the top and ask what kind of things could we possibly write down, which could give us something which at the bottom could play the role of the longitudinal component of the W, you would basically build exactly the same story. I was emphasizing it from the bottom up just to show how there's essentially no choices at every stage.
So there's a question on the left.
Yes.
Using these arguments, what can you say about the three halves, the existence of three halves?
Well, I'll just say one very short thing about it.
In which units?
Yeah. In 1 minute in ordinary units. I told you that we went through this argument that spin zero is just forced on, right? But it's very weird. It's nonetheless very, very weird. And it's very weird because unlike all the higher spins, which for a very, very simple reason I could explain over wine and cheese, we can understand why they're essentially massless, or they're so light compared to some truly fundamental scale like the Planck scale. We cannot explain and understand why the spin zero particle has that property. It's a very basic piece of mathematics. It's that 2 is not equal to 3, but 1 equals 1. Okay? Because 1 equals 1, we can't actually. It's very, very mysterious why this guy should be lying around at scales much, much smaller than the Planck scale or some other scale. And that's a very serious mystery. That's a very serious mystery that's been appreciated and understood for 30 years. And people have tried to solve that in a variety of ways. They try to make the Higgs, some people try to make the Higgs again itself a composite of other things that turns to mush at high energies. You don't learn your lesson once, you try to do it again and again. Okay? But it's very unlikely, I think. I mean, it's not ruled out, but it's very unlikely that is the picture. But we can now look and see, is there anything we haven't used? That's a guy we haven't used. I told you that if there's the spin 3 halves guys around, they've got to be incredibly special. See, things get more and more special as you go up. This is completely unique. It's the graviton. This is not totally unique, but still, if it exists, there has to be a very, very special structure for all the rest of the particles, and that structure is supersymmetry. Okay? And that's the reason why a lot of theoretical physicists are excited about supersymmetry. It's because it's the last thing nature can do that consistently do that we haven't seen it use yet. Okay? We've seen it use everything else now. You're brave enough to say you should see 0 when you haven't seen it before, you see it. There's one last thing that it can do, which is to use that. And remarkably, again, it's a very, very simple reason. If it's around, it can greatly ameliorate explaining why it is that this Higgs is around to begin with.
All right,
So,
thank Nima one last time. Thank you.